Alrighty. Hello everyone. Yeah. Is everything working? Alrighty. Okay, I see my screen. Okay, welcome to part 2 of MathSoc's 1081 revision seminar. We will be going into combinatorics today. Yeah. So we're going to start off with an easy one. Let x1, y1 for xi, yi for I is equal to 1, 2, 3, 4, and 5 be 5 distinct points in the plane with integer coordinates. Prove that at least one midpoint of 2 such points has integer coordinates. So, to do this question, we will be using Pigeonhole principle. And this is a picture that one of our lovely education directors took at the Easter show for the purposes of this revision seminar, I believe. Yeah, so Pigeonhole principle is that given that there are n+1 pigeons sorted across n pigeonholes, then there is at least one pigeonhole with 2 or more pigeons. So the generalized pigeonhole principle is that with n pigeons and k pigeonholes, there is at least one pigeonhole with the ceiling function of n on k or more pigeons. So going back to this question, if we think about what the midpoint of A, B, and CD, 2 coordinate points are, the general form would be A plus C on 2, B plus D on 2. And to have the average of 2 integers also be an integer, they must be either both odd or both even. So therefore, we need to have A and C with B and D be the same parity, so both odd or both even. So if we consider all the different combinations of parity for x and y, that would be odd and odd, even, and odd and even. And since we have 5 distinct points here, with only 4 possible cases of parity, by Pigeonhole principle, there must exist 2 points which share parity for both coordinates. So essentially, there must be, with the 5th point, another point that has the exact same parity as these 4 possibilities given. So these 2 points, the repeated one and the original one from these 4, would make a midpoint with integer coordinates. Going on to the next question, how many different ways are there to distribute 80 identical boars and 40 distinct lollipops among 8 children? Part A, with no further restriction, and part B, with each child getting at least 1 boar and exactly 5 lollipops. So, starting off with part A, considering no further restriction, we must split the problem into 2. So part 1 would be distribute 80 identical boars among 8 children. And part 2, distribute 40 distinct lollipops among 8 children. So we can get the answer to part A by multiplying the answers we get for each of these subproblems, because these 2 are independent events, and we know that multiplying them together will give us the probability or number of different ways that these 2 events can occur at the same time. Okay, so distributing 80 identical boars among 8 distinct children. We can represent the amount of boars each child gets by xi. And so x1 plus x2 all the way until x8 is equal to 80, where xi is a non-negative integer. So starting from 0 and going up in whole numbers, because you can't have less than 0 objects. So the general solution for n identical objects and r distinct boxes is n plus r minus 1 C R minus 1. So this is the general solution that you can derive from pretty much stars and bars. But if we sub these in where there are R is equal to 8 children, so boxes or bars, and N is equal to 80 objects or stars, then we get 80 plus 8 minus 1, C 8 minus 1. So 87, C 7. Keeping in mind that this formula only works when xi is greater than or equal to 0. So, part 2, distributing 40 distinct lollipops among 8 children. So the general solution for n distinct objects and r distinct boxes is r to the power of n. What's essentially happening here is we are considering this scenario from the perspective of the lollipop. With 40 different lollipops, and each lollipop having the choice of these 8 children to go to, that would be 8 times 8, 40 times, giving us 8 to the power of 40. So now that we have these two scenarios, we have 87C7 different ways to distribute the 80 identical balls, and 8 to the power of 40 different ways to distribute the 40 distinct lollipops, multiplying them together. Hence, there are 87C7 times 8 to the power of 40 different ways to distribute the objects among 8 children. So that's part A done. Moving on to part B, pretty much similar approach, splitting the problem into 2 different parts. So part 1, distributing 80 identical balls among 8 children, where each child must get at least 1 ball. And then part 2, distributing 40 distinct lollipops among 8 children, and each child getting exactly 5 lollipops. So again, we can multiply these 2 answers together to give us the final solution for part B. So we can represent the amount of balls each child gets by xi. So same equation here, x1 plus x2 all the way until x8 is equal to 80. Except here, xi must be a positive integer, so it cannot be equal to 0, and it must be greater this time. This general solution for n identical objects and r distinct boxes is n minus 1, c r minus 1. So again, stars and bars, but you can't have the bars be next to each other because that would create a scenario where some of the children have 0 balls. So subbing in r is equal to 8 children and n is equal to 80 balls, we get 80 minus 1, c 8 minus 1, which is equal to 79, c7. Yep, so part 2 of the problem, distributing 40 distinct lollipops among 8 children, where each child has to get exactly 5 lollipops. So here we can have each child choose 5 lollipops from the pile. So the first child has 40 lollipops to choose from, and they must choose 5, meaning that they have 40 C5 ways to choose. And then after that, the pile of lollipops will decrease by 5. So each successive child will have 5 less to choose from, giving the second child, for example, 35 C5 different ways to choose their 5 lollipops. And as this goes on, the 8th child will only have 5 lollipops to choose from, and they must choose 5 from them, giving us the last one at the end, 5C5. Multiplying these all together are the number of ways you can distribute 40 distinct lollipops such that each child gets 5. All right, so we know that the factorial form of NCR is equal to n factorial on n minus r factorial times r factorial. So writing this expression in its factorial form, we would have what we have on the right-hand side, so 40 factorial on 35 factorial times 5 factorial, and so on. As this goes on, we see that the numerators will cancel out with some of the denominators, leaving us 40 factorial on top and 5 factorial remaining from each of the 8 denominators. And so therefore, there are 40 factorial on 5 factorial to the power of 8 ways to distribute. And so, since we know from part 1 that there are 79C7 different ways to distribute the 80 identical Bohrs, and from part 2 that there are 40 factorial on 5 factorial to the power of 8 different ways to distribute the 40 distinct lollipops, multiplying them together, we get 79C7 times 40 factorial on 5 factorial to the power of 8 different ways to distribute the objects among the 8 children where these restrictions apply. Okay, so the next question, consider the equation x1 plus x2 all the way until x6 is equal to 36, where xi, x2, all the way until x6 are non-negative integers. So how many solutions are there with all the xi being odd and xi being less than or equal to 7? All right, so we want to make it so that each term can be represented by consecutive integers instead. And being odd restricts this because they must all be split by at least 2. So we can't have a range like 0, 1, 2, 3, and must adhere to 1, 3, 5, and so on. So another way of writing the odd expressions as consecutive would be rewriting xi is equal to 2yi plus 1, where yi is an integer. And we know that xi must be greater than or equal to 0 because it cannot be 0 since it is odd, and so thus xyi plus 1 is greater than or equal to 1. And so yi has a restriction that it must be greater than or equal to 0. And because the question also gives us the restriction that xi must be less than or equal to 7, subbing that into the inequality, 2yi plus 1 is less than or equal to 0, hence we are left with yi must be less than or equal to 3. So, using this substitution and subbing in all the y's into this left-hand side, and then factorizing them out so that we have 2 times y1 plus y2 plus y3 all the way until y6, and then plus 6 at the end is equal to our right-hand side. By rearranging this equation and making the summation of y as the subject, we get this is equal to 15. Okay, so we have boiled down this really complicated question into this much simpler one, and we just need to solve this equation now. All right, so now that we know that it can be written in this form, we need to find how many solutions are possible where all of the yi are less than or equal to 3. So we can look at the total minus the complement, because we know that the amount of solutions for all yi is less than or equal to 3 is equivalent to the total number of solutions minus the solutions where some of the yi are greater than 3. And from the formula before, with no restrictions, there are a total of 15 plus 6 minus 1, C6 minus 1, so 20C5 solutions for the equation above when there are absolutely no restrictions other than must be greater than or equal to 0. Okay, so to find the solutions for the complement where some of the yi are greater than or equal to 4, we need to find out when there is one such y, when there are two such yi, and where there are three such yi. And the reason why we can't go on and consider the case where there are 4 such yi, it's because if there were 4 of these greater than or equal to 4, then it would total up to 16, and then we would have yi plus yi is equal to -1, and because they both need to be positive, then there's no way that could happen, which is why we only go up to 3. Okay, so looking at the scenario where there is 1 such yi, we consider the case that y1 is greater than or equal to 4. So we're going to make the substitution that y1 is equal to a1 plus 4, and every other yi is equal to ai. And subbing this into the equation, we get a1 plus 4 is, plus a2 plus a3 all the way until a6 is equal to 15. And rearranging, we get that the summation of the 6 a's is equal to 11. So the total number of solutions here would be 11 plus 6 minus 1, C6 minus 1. So essentially 16, C5. Okay, now for 2 such yi, pretty much the same thing. We consider that y1 and y2 are both greater than or equal to 4, and we'll need to make 2 substitutions this time. So same things are happening, subbing the a's in and then rearranging to get the value of the a summation to find the total number of solutions to be 12C5. And exactly the same happening for the case where there are 3 such yi greater than or equal to 4, which gives us that the total number of solutions for this case is 8C5. Okay, so we will now need to use the inclusion-exclusion principle to solve this question, because in our case, where ai represents when yi is greater than or equal to 4, then there are going to be cases where there is 1 pronumeral that's greater than or equal to 4, but there could also be more. So we've definitely overcounted in our steps, and we're going to need to make up for those cases. So using the inclusion-exclusion principle, if you go into it and then add all those cases together and then subtract the pair solutions from happening, and when that happens, you're also going to be overcompensating and getting rid of some of the cases where there are 3 cases where there are pronumerals greater than or equal to 4. And so adding those back in, we get the final line. And if you sub in all of the answers that we got from our previous parts in this question, then you'll find that there are a total number of 86 solutions. Okay. So moving on, let S be the set of all 14-letter words from the 26 letters of the English alphabet, where no letter is used more than once. So, part A, how many such words are there altogether? Part B, how many words in the set contain the subwords Julia or Tony? And part C, how many words in S, the set, contain all 5 vowels? Okay, so part A, how many such words are there altogether? Because we have 26 letters where repetition is not allowed, then we are just choosing 14 letters from these 26 and then counting the number of ways that they can be ordered. So that would just be a classic permutation, and subbing 26 and 14 in, we get that there are 26p14 words altogether. Part B, how many words in the set contain the subwords Julia or Tony? Okay, so again, a slight use of the inclusion-exclusion principle. So the cases that contain the words Julia and Tony are going to consist of the words that only consist of Julia, only consist of Tony, and then it's going to overcount the scenarios where the word has both Julia and Tony within it. And so we're going to have to account for that. And to find the total number of words with Julia or Tony, we're going to need to find each of these different values. So that would be the words with Julia, or the words with Tony, and then all the words that have both Julia and Tony. Okay, so starting off with finding the words with Julia, we consider where those 5 letters have already been chosen. So within the 14-letter word, there are 9 empty spaces left for the remaining 21 letters of the alphabet, because repetition is not allowed. So because there are 21 letters to choose from and then 9 spaces to fill, that would be 21C 9 ways to choose these letters. And now to arrange these, because Julia, the words are going to have to be together, we need to preserve the order. We're going to consider it as an element. And so if Julia takes up 1, that gives us the 9 remaining letters as the other elements in this word. And so there are a total number of 10 objects, and so 10 factorial arrangements. So considering for the different letters that can be chosen and the arrangement of them, there are a total number of 21C9 times 10 factorial words with Julia. And pretty much the same deal with Tony. So Tony, 4 letters have already been chosen, so there are 10 spaces left to fill with the 22 remaining letters in the alphabet. And so there are 22C 10 ways to choose these letters. To arrange these, again, we want to preserve the order of the subword Tony. So we're going to treat these 4 letters together as one object, and then all of the 10 remaining letters that aren't Tony as other objects. So a total number of 11 objects and 11 factorial arrangements coming from those. So multiplying these together, there are 22C10 times 11 factorial words with Tony. Alrighty. And to find the number of words with Julia and Tony, we're going to consider, okay, Julia has already been chosen, Tony has already been chosen, which gives us 9 letters out of the 14 letters in the word having been chosen. So there are 5 spaces left and 17 letters left in the alphabet to choose from. So there are 17 C5 different ways to choose which letters will fill these spaces. Because we want to preserve both Julia and Tony, they're both going to be treated as objects. So Julia is one object, Tony is another object, and the remaining 5 letters are also going to be objects. And so there are 7 objects altogether, giving us 7 factorial different arrangements. And multiplying the different letters that could be chosen and the different arrangements, there are therefore 17C5 times 7 factorial words with both Julia and Tony. Okay, cool. So going back to our formula from the inclusion-exclusion principle, the number of words that would contain Julia or Tony, so the union of all of those situations, is equal to the number of words that contain Julia plus the number of words that contain Tony, subtract the number of words that contain Julia and Tony, because those scenarios would have been double counted. And so therefore, there are 21C9 times 10 factorial plus 22C10 times 11 factorial minus 17C5 times 7 factorial such words. Okay, Hope that made sense. Yeet. Okay. Now moving on to part C. How many words in the set S contain all 5 vowels? Okay, so we suppose that all 5 vowels have already been chosen for the word. So that means there are 9 spaces left in the 14-letter word to fill, and there are 21 consonants left over since there is no repetition. So there are 21 C9 ways to choose the rest of the letters that will go into this word. And we just need to arrange the 14 letters that have been chosen. So that would be 14 factorial different arrangements because, you know, the vowels aren't particularly picky. They don't need to be in a specific arrangement. So that would just be 21 C9 times 14 factorial words in the set S that contain all 5 vowels. Okay, cool. So, next question. 4 friends, June, Alex, Wayne, Joe, are playing a hand of bridge. A standard pack of 52 playing cards are dealt, giving each player 13 cards. Part A, find the probability that June and Wayne are dealt all 13 spades. And part B, find the probability that the cards dealt to June and Wayne contain at least one complete suit. Okay. So part A, find the probability that June and Wayne are dealt all 13 spades. So between June and Wayne, they should have 26 cards because each player is dealt 13 cards. And so the cases where all 13 are dealt to them mean that 13 of those cards must be those 13 spades. So there are 13 possible cards remaining that must be in their hand that aren't spades. So within the 39 remaining cards in the deck that aren't spades, 13 of them must be in June and Wayne's hand. So we're just choosing the different number of possibilities that those cards, like what they could be. So the number of cases that would be 39C13. And so the probability would be given by 39C13 on 52C26. Yeah, okay. Sorry, that was probably a bit confusing, but whoops. Okay, part B, find the probability that the cards dealt to June and Wayne contain at least one complete suit. So from part A, we know that there are 52C26 total cases, so that's our denominator sorted. And this is another application of the inclusion-exclusion principle. So from part A, we know that the number of cases to get a single complete suit is 39C13, and this should be the same across all the different suits, so spades, clubs, diamonds, hearts. That number will not change. There is only one way to get 13 spades and hearts dealt, since there are only 26 cards between June and Wayne. And so because there are only 26 cards, there's no way to get, 3 or even 4 complete suits. That would require 39 or more cards to be dealt between June and Wayne. And so, applying the inclusion-exclusion principle, the number of cases where a complete suit is held is equal to the number of cases where June and Wayne have all the hearts, plus all of the clubs, plus all the diamonds, and then subtract the pairs where that's happening because those cases will be overlapped. And we don't need to account for when they have 3 suits or 4 suits because that's just not possible within the parameters of this question. So this is equal to 4C1 times the number of ways that they can get all of the spades because the probabilities are the same across all the 4 suits, minus 4C2 because that's the number of different ways the pairs can occur, multiplied by the intersection of those cases happening. And because we know from earlier that this is just 1, our final answer simplifies down to 4 times 39C13 minus 4C2. All right. And because the question is asking about the probability of this occurring, we must consider the total number of possibilities this could have occurred from. So what we just got there was the numerator, and our denominator is the total number of possibilities, so 52C26. All right. Okay. Consider the set of all n-digit numbers formed by the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let an be the number of such numbers containing an odd number of prime digits, and let bn be the number of all such numbers containing an even number of prime digits. So part A, write bn in terms of an, explaining your answer, and part B, obtain a recurrence relation for an, again, explaining your answer, but you do not need to solve this recurrence relation. Okay, sweet. So part A, write bn in terms of an. So because an n-digit number must either have an odd or even number of prime digits, the sum of an and bn must be equal to the number of all n-digit numbers that can be formed with the digits available, because there's no room for overlap or undercounting. So as any of the 9 digits can be used with repetition, the number of n-digit numbers that can be made would be 9 to the power of n. Meaning that the relationship between an and bn would be an plus bn is equal to 9 to the power of n. And because the question wants us to write bn in terms of an, we'd rearrange this to make bn the subject, getting bn is equal to 9 to the power of n minus an. Okay, moving on to part B, obtain a recurrence relation for an. So we're going to consider an minus 1 and bn minus 1. So that would be the an minus 1 being the number of n minus 1 digit numbers containing an odd number of prime digits, and bn minus 1 being the number of n minus 1 digit numbers containing an even number of prime digits. So if we add them together, they must account for every single n minus 1 digit number with no overlaps and no overcounting. Wait, no overlaps and no undercounting, yeah. Okay, so in the case of an minus 1, in order for it to contribute towards an, it must retain the same number of odd prime digits, because it already has an odd number of prime digits as an n minus 1 digit number. And so in order for it to become a part of an, it must gain another digit, and that digit must not be a prime, so that it can continue having an odd number of prime digits. And 5 digits within the set of digits 1 to 9 fit this criteria. So that would be 1, 4, 6, 9. In the case of bn minus 1, the number of n minus 1 digits with an even number of prime digits. Again, in order for that n minus 1 digit number to become an n digit number, it must gain another digit, and that digit must be a prime number for it to do that, to become a minus 1, a part of an, because it already contains an even number of prime digits, and it must have an odd number of prime digits for it to contribute towards an. And so the nth digit must be a prime, and 4 digits would fit this criteria. So, oh, Lord. It appears I have wiped the solution for this one. Okay, all right, that's fine. All right, so what happens essentially is the answer would be an is equal to 5 times an minus 1 plus 4 times bn minus 1. And from part A, because we wrote bn in terms of an, we can write bn minus 1 in terms of an minus, well, kind of. Okay, in terms of an minus 1. Yeah. And so making that substitution and then just simplifying a bit, in the end, I think we're going to get, what was it? an minus 1. an minus 1 plus 9 to the power of n minus 1, I believe. Not certain, but I don't know. It was just some calculations on the next slide, but you should be fine. I believe in you. Okay, you got this. Cool. All right. Next, obtain the general solution to the recurrence relation an minus 6 an minus 1 plus 9 an minus 2 is equal to 5n times 3 to the power of n. Okay, so going through the definitions for recurrence relations, so below is the general recurrence relation of order k in this form, where f of n and ci are functions of n. And there are some properties, so all ci are constants when it's linear. When it's homogeneous, f of n must be equal to 0, and when it's non-homogeneous, f of n is not equal to 0. Okay, so just some things to be aware of, and these are the different solutions to characteristic polynomials in different cases. So where alpha and beta are roots of r squared plus pr plus q is equal to 1, so the characteristic polynomial. If alpha and beta are real and non-equal, then this would be their general solution. If they're real and equal, then this other one would be the general solution. So there are just different things to do when these roots are of a different form. All right? Choose your own adventure. Okay. And when it is a non-homogeneous solution, so pretty much when f of n is not equal to 0, then there is going to be a particular solution that must also be accounted for, and it can be guessed by mirroring the form of f of n. So if it's a constant, and it's going to be a constant. If it's a polynomial, then it will probably be a polynomial of the same degree, and so on. Just some, you know, a cheat sheet to work off of, some things to be aware of. Okay, so going into this question, we can see that this is a non-homogeneous linear second order recurrence, meaning that the solution of the relation would be in the form an is equal to hn plus pn. So the solution of the non-homogeneous relation is equal to the solution of the homogeneous relation plus our particular solution. And so the homogeneous recurrence for this relation is an minus 6 an minus 1 plus 9 an minus 2 is equal to 0. So looking at our polynomial, r squared minus 6r plus n is equal to 0, where the solutions are r is equal to 3 and 3. So we have a double root at 3. So if we remember back to what we would do in this scenario, then the general solution would be given by a times 3 to the power of n plus bn times 3 to the power of n, since the solutions for the quadratic are the same. Okay, so now that we've identified the solution of the homogeneous relation, we also have to account for the particular solution. And so if we look at f of n in this case, that would be 5n times 3 to the power of n, and we want to mirror this function, which is linear and also an exponential with a base of 3. So it must fit in the form cn plus d times 3 to the power of n. And we can expand it here, but yeah, c and d must be real numbers. So the particular solution only works if it does not share terms with the homogeneous general solution. And since cn times 3 to the power of n is the same as bn times 3 to the power of n, this particular solution does not work. Moving on, our next try for a particular solution would be found by multiplying n to our old one. So that would be n times cn plus d times 3 to the power of n. And then expanding that, this gives us dn times 3 to the power of n plus cn squared times 3 to the power of n. But it has a term, dn times 3 to the power of n, which again is the same as bn times 3 to the power of n, so this would also not work. Okay, we're going to try again, third time lucky. Instead, we're going to try using pn is equal to n squared times cn plus d times 3 to the power of n. So to find the constants of our particular solution, you would use pn in place of an, and so subbing it in and expanding it is going to be really long. So simplifying this expression by factorizing out 3 to the power of n minus 2 and then collecting all the like terms, we're going to be left with equations. So 6cn minus 6c plus 2d is equal to 5n. And if we equate all of the coefficients of n and the constants, then we get 6c is equal to 5, and 2d minus 6c is equal to 0. And solving these, c is equal to 5 on 6, and d is equal to 5 on 2. Therefore, our particular solution is equal to n squared times 5n on 6 plus 5 on 2 times 3 to the power of n. Yay! Okay, so now that we've found our particular solution, we can add it to our general solution, meaning that the general solution for this entire recurrence relation, the non-homogeneous one, is equal to an is equal to a times 3 to the power of n plus bn times 3 to the power of n plus n squared times 5 on 6 n plus 5 on 2, or times 3 to the power of n. All right, very cool. Okay, well, that's it for my section. And Lockie will be taking you guys through graph theory. All right. Please let me know if you have any questions regarding my section. I'll try my best to answer them. Yeah.
Okay, I should be live now, so let me know if there's any problems, but um, thank you to Mary for going through combinatorics, and now I'll be going through graph theory, which is the last topic in Math1081. So the first thing I'm going to go through are a few graph definitions. So the degree of a certain vertex V, oops, the degree of a certain vertex V is the number of edges incident to it. So if I had a particular vertex V here, and I had these edges incident to it, then I would have 3 edges incident to it, therefore the degree of this particular vertex would be deg V equals 3. And a vertex degree sequence is just a non-increasing sequence of all the vertex degrees in a graph. Now, an important relationship between edges and vertices is the handshaking lemma. So it says that if I sum up all of the degrees of all the vertices in the graph, then I will get 2 times the number of edges. So this thing on the right hand side represents the cardinality of the edge set, i.e. the number of edges. So let's go ahead and look at a question from the 2021 Term 1 exam. Now, it gives us 3 different degree sequences. So the question is, can graphs with these degree sequences exist? And if they do, can they be simple? So simple means we're not dealing with a multi-graph. So no repeated, no parallel edges or loops. So let's look at the first example. Can this following graph exist? Well, the only way that a graph with a certain degree sequence wouldn't be able to exist is if the sum of all the degrees was not an even number. Why is that the case? Well, if we look at our handshaking lemma, we know that if I add up all the degrees of the vertices, then I get twice the number of edges. Now that means, and because the number of edges is an integer, that means that if I sum up all the degree vertices, then if it's not an even number, then the graph cannot exist. Okay, so if I add up all of these numbers, all of these following vertex degrees, then I get 25, which is an odd number, which means that the graph cannot exist because we have an odd sum of degrees, and by the handshaking lemma, we are supposed to get an even number. Hence, the graph can't exist. Okay, so for the next part, can this graph with this degree sequence exist? Well, first thing we want to do is do the same thing. We want to check whether if I add up all the degrees, do I get an even or odd number? Well, in this particular case, if I add them all together, I just get 3 times 6, okay, which is an even number, and hence this graph can exist. Now the question is, can it be simple? Well, to prove that a simple graph can exist with this degree sequence, all I need to do is construct the graph. Okay, so if I can construct a graph with this degree sequence and show that it's simple, then I've proven that a simple graph can exist with this degree sequence. So how am I going to construct that graph? What is the thought process? Well, I have 6 vertices. Okay, so I'm just going to first plot down 6 vertices. Okay, and I'm going to label them 1, 2, 3, 4, 5, 6. Now, I know that the degree of every single vertex is 3. Okay, the degree of every single vertex is 3. So if I start with a particular vertex, say 1, what I can do is connect it to its neighbors, okay? Which means that the degree of 1 is now 2. Now, what I can do is connect to the vertex opposite 1, okay, to get to 4. And that means that the degree of 1 is now 3. Why did I do that? Well, if I look at the vertex 4, if I did the same process and connected it with its neighbors, okay, notice that immediately I've now got the degree of 4 is 3. Okay, so just by doing that, I've now created 2 vertices with degree 3. Now, if I look at 6, for example, I can do the same process. I connect it with its neighbors. It's already connected to 1. Now I need to connect it to 5. Okay, and then I connect with the vertex opposite to it. Okay, and now suddenly the degree of 6 is 3. Now, let's look at 5. 5, the degree of 5 is 2. So I'm going to connect it to its opposite, okay, which is 2. And now if I simply just connected 2 and 3, notice that the degree of every vertex is now 3. So 1, 2, uh, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay, so this is a following graph that has the degree sequence that is listed in the question. Okay, and this is a simple graph because there's no loops or parallel edges, therefore the graph does exist. Therefore graph exists. Now the last part of this question is can this graph with this degree sequence exist, and if so, can it be simple? Well, if I check the sum of the degrees, okay, I would also get an even number, so the vertex sum is even. Now, if I have a suspicion that this is not a simple graph, how can I prove that? And why would I even think of that in the first place? Well, one thing to notice is that we have a total of 1, 2, 3, 4, 5, 6, 7. Okay, we have a total of 7 vertices. Okay, notice that if we're dealing with a simple graph, a vertex can't be connected to itself. Can't be connected to itself. So no loops. That's equivalent to saying there is no loops in the graph. Okay, so let's suppose a simple graph with this degree sequence does exist. Now, I know that there's no loops, okay? Now, if I look at this, I have 3 vertices with degree 6. 3 vertices with degree 6. Okay? Now, something to notice is that if they have a degree 6, that means it needs to be connected to every single other vertex in the graph. Okay? Again, that's because there's no loops. There's a total of 7 vertices. If a vertex has degree 6, it must be connected to every single other vertex in the graph, not including itself. What does that mean? Well, notice that we have a vertex with degree 2. Okay? But we have 3 vertices with degree 6. Because we have 3 vertices with degree 6, all 3 of these vertices need to be connected with every other vertex in the graph, including this one with degree 2. But that's a contradiction. Why? Because if we have a degree of 2, that means it's only connected to 2 other vertices. However, if all of these are degree 6, all 3 of them need to be connected to this vertex with degree 2. Okay, so how do I write this out more rigorously? Well, what we can do is suppose that a graph G existed with this degree sequence, and we can label the vertices as v1 up to v7. Now, because the degree of v1, v2, v3 is 6, they need to be adjacent to every other vertex in the graph. And specifically, the degree of v7 must be at least 3, because it needs to be adjacent to v1, v2, and v3. However, this contradicts the degree sequence of G, hence G cannot be simple. However, a multigraph of it can exist. A multigraph could exist because we could have a loop that would make this argument null. So let's move on to another definition. So this is the definition of a bipartite graph. Okay, a graph G is bipartite if there are 2 disjoint sets v1 and v2 such that the union of the 2 sets gives the vertex set, and every edge of G connects a vertex in v1 to a vertex in v2. So in loose terms, we can kind of think of a graph being bipartite if every other vertex in one subgroup only connects to vertices in the other subgroup. Okay, so let's look at some small examples here. So an easy example would be the complete bipartite graph K32. So K32 will have 3 vertices in one set and 2 vertices in the other set. Okay, so I'm going to consider the top row to be my first disjoint set V1, and the bottom row can be my second disjoint set V2. Now, for a bipartite graph, vertices in V1 can only connect to vertices in V2, and similarly, vertices in V2 can only connect to vertices in V1. Okay, so if we look at creating the complete bipartite graph, what we need to do is connect this vertex in V2 to every other vertex in V1, but not to a single vertex in V2. Okay, similarly, we could do the same with this, okay? And you would see that we're actually complete, because if I look at a particular vertex in V1, so this one is connected to the two vertices in V2. Okay, but we could also get other types of bipartite graphs. For example, we could have something like this. Okay, so this is maybe my first. Actually, wait, we'll say that this is my first vertex set V1, and this is my second vertex set V2. Okay, so vertices in V1 can only connect to vertices in V2. Okay, so this would be an appropriate bipartite graph. So this is also a bipartite graph. Okay. Now we have a theorem about bipartite graphs. A graph is bipartite if and only if it contains cycles of even length. Okay, so what are cycles? Well, let's look at some more definitions. So the more precise definitions of walk, trail, circuit, path, cycle, etc. are in the lecture notes, but I've got a sort of summary of the main information that you need to know. So a walk can be closed or open. Edges can repeat, vertices can repeat. So in terms of closed open, that means if it's closed, then it needs to start so it needs to end at where it started. Open, it doesn't matter. Now for a walk, edges can repeat, vertices can repeat. But for a trail, we don't repeat edges and we can repeat vertices. For a circuit, we don't repeat edges and we can repeat vertices. Now for a path, no repeated edges, no repeated vertices, and a cycle, no repeated edges, no repeated vertices. And a circuit can be closed. A circuit has to be closed. A cycle has to be closed. Trail has to be open, and a path has to be open. Okay, so you can look at this in your free time if you want to sort of remember all of these definitions. Now, there are two types of paths and circuits that we are really interested in. We are interested in Euler paths and Euler circuits. Okay, so what is an Euler path? Well, it is a path that passes through every graph in a G once. And a connected graph G has an Euler path if and only if there are exactly two vertices of odd degree. Okay, so let's look at an example of an Euler path. So an Euler path, this is a particular example of an Euler path. So if we look at this graph G, okay, an Euler path needs to pass through every single edge in the graph. Okay, so if we label these, say A, B, C, D, E, let's think about what an Euler path for this graph might look like. Well, we can start at A, get to B, from B we can go to C, C we can go to D, D we can go to E, and E we can go to C. Okay, notice that we've used every single edge in the graph. Okay, so the path A, B, C, D, E is an Euler path. Okay, and let's look at that condition for an Euler path to exist. It says if and only if there are exactly two vertices of odd degree. Notice that the degree of A equals 1 and the degree of C equals 3. Okay, and every other vertex has an even degree. Okay, so you can see that that condition holds in this particular case. Now an Euler circuit is a circuit, so it needs to end where it started. It needs to be closed. That passes through every edge in the graph G once. So Euler means it needs to pass through every edge. Path means it has to be open, and circuit means it needs to be closed. Now the condition here is that a connected graph G has an Euler path if and only if there are only even vertex degrees. Okay, so let's look at a particular example of an Euler circuit. So this should be circuit. So let's consider this graph here, right? With these edges, with this edge set. Again, let's just label things A, B, C, D, E. Now, an Euler circuit, needs to end where it started, and it needs to pass through every edge. So let's start with A, and from A we can go to B, B we can go to C, C we can go to D, D to E, E to C again, and C to A. Okay, so if we look at a circuit can have repeated vertices, so something like this is allowed. Now, so the path A, B, C, D, E, C, A is an Euler circuit. Notice that we've used every single edge in the graph. we've used up every single edge. Euler circuit. Okay, so that's a particular example of an Euler path and Euler circuit. Now let's move on to Hamiltonian path and circuit. So a Hamiltonian path is similar, except instead of passing through every edge, it needs to pass through every vertex. So we need to pass through every vertex of the graph exactly once. Now, unfortunately, there's no easy criteria for a Hamiltonian path. But one thing to notice is that a Hamiltonian path or circuit uses at most 2 edges incident to each vertex. Why is that the case? Well, if I had a particular vertex like this, and I had edges here, here, and here, let's look at a Hamiltonian path. So a Hamiltonian path can come in and then out. It has to come in and out, right? Say we use this other edge here, okay? What would that mean? Well, we can come in and out, and then at some point we might go use this purple one. Actually, so for example, if it was like this, so that purple one, if we use that purple one, then that purple one brings us back to the vertex. Okay, and the problem with that is we need to pass through the vertex exactly once. That would mean we're passing through the vertex twice. Okay, so one criteria we can use is that we can kind of think of a Hamiltonian path as having to go in and out. Okay, so it uses at most 2 edges incident to each vertex. So a particular example of a Hamiltonian path might be with this graph here. So if I have a graph looking like this, okay, Hamiltonian path needs to pass through every vertex. So a particular example might look like this. So we start from here, we go here. So we start from here, go to here, go to here, go to here. Okay, notice that we've used every single vertex exactly once. Okay, we don't have to use every edge. So that's a particular Hamiltonian path. And notice that the Hamiltonian path uses at most 2 edges incident to each vertex. Now a Hamiltonian circuit is similar, except it needs to be closed, so it needs to end where it started. So it's a circuit that passes through every vertex in the graph G exactly once, except for the first and last, because they overlap. Now, in terms of conditions, again, we don't have an easy criteria. However, if a graph G has a Hamiltonian circuit, then the circuit must include all edges incident with vertices of degree 2. Okay, so that's what that is saying, is that if I have a particular vertex that has degree 2, okay, what it's saying is that the graph needs to go in and out. Okay, why is that the case? Well, in the case with a Hamiltonian path, you can see that we could end at this vertex, at the top vertex. Okay. However, because the Hamiltonian circuit needs to return where it started, we can kind of think of it needing, if it goes through an arbitrary vertex, it needs to go in and out. It can't just go in. It has to go in and out. Okay. Yeah. So now, if G is a connected and simple graph with greater than 3 vertices, such that each vertex has degree n on 2, then G has a Hamiltonian circuit. So that's a useful condition that we can remember. However, it's not a just because a graph doesn't meet this criteria. If a graph doesn't meet this criteria, then it could still have a Hamiltonian circuit. Also, something I don't think I emphasized enough was that for a Euler path to exist, okay, we need the graph G to be connected. Okay, so these conditions, so if and only if there are exactly 2 vertices of odd degree, that is dependent on the graph G being connected. Same with Euler circuit, it needs to be connected. So connected just means that you can get to any vertex from any other vertex. Yeah. So now let's look at a particular example here. So 2019 term 2 question 1 part 2. So what we have is this particular graph G. Does the graph G contain an Euler path? Is G bipartite? And C, prove that G does not contain a Hamiltonian circuit. Okay, so how do we go ahead and tackle this question? Well, for part A, Okay, does G contain an Euler path? Well, let's look at our condition for an Euler path to exist. First of all, the graph G needs to be connected. It needs to be connected. And second, it needs to have only two vertices of odd degree. Exactly two vertices of odd degree. Okay, so first of all, we can see that the graph is connected because we can get to any point from any other point. Okay, now let's look at the degrees. Okay, so let's look at the degrees. So in this case, let's look at the degree of y. So degree of y equals, so let's count the degree of y. So it's going to be 1, 2, 3. Degree of y is 3. Okay. Now let's look at degree of x. Okay, degree of x. So the degree of x is 1, 2, 3. So degree of x is 3. Now we have two vertices of odd degree. Okay, we have two vertices of odd degree. That means we can't have any more vertices of odd degree. Any more, and an Euler path won't be able to exist. So let's keep counting. So let's look at W. 1, 2, 3, 4. Okay, that's fine. That's even. Let's look at V. 1, 2, 3, 4, 5. Okay, degree of V equals 5. Okay, and because there are greater than two vertices of odd degree, Euler path can't exist. Euler path cannot exist. So the answer to A is no, an Euler path can't exist. Now part B is G bipartite? Okay, is G bipartite? Well, one way to tackle this question would be to look at vertices which can't be in the same set. So look at vertices which can't be in the same set. So vertices that can't be in the same set, well, clearly y can't be in the same set as x, okay? Because they're connected like that. Which means that what we have to do is put them into two different sets, okay? Now, obviously, w can't be in the same set as x, so we're going to put it in the purple set. Now, something to check is whether w is adjacent to y, and the answer to that is no. So we haven't caused any problems here. Now, v obviously needs to be in the other set, okay? Now, is v adjacent to x? And the answer is no. Okay, so we can keep going. Now, t has to be in the other set, obviously. Now, t isn't connected to w, and it's not connected to y, so it's not adjacent to w or y. Hence, we haven't caused any problems. Now, what about s? Well, s is got to be in the other set because it's adjacent to t. So we're going to put it here. And now, luckily, s isn't adjacent to v or x. Now, for r needs to be in the other set, obviously, because it's, again, adjacent to s. And now, r is only connected to vertices in the blue set, so we're okay again. Now, q needs to be in the blue set. Q is not connected to any other vertices in the blue set, so again, we're good. Now, P needs to be in the purple set, and again, if we look at the vertices P is connected to, Q and V, we're okay here, okay? Because it's not connected to any other purple. Now, that means what we have done is constructed two sets. Okay, we've constructed two sets, namely Y, W, T, R, P, R, one sec, RP, and we've constructed the set X, V, S, Q. Okay, so notice that sets in, vertices in the first set are only adjacent to vertices in the second set, and vertices in the second set are only adjacent to vertices in the first set. Hence, we've constructed two sets, two just joint sets that that allow us to conclude that the graph G is bipartite. So to prove that to prove that a certain graph is bipartite, all we need to do is find a bipartition of V of G. Okay, so to prove that it's bipartite, all we need to do is find a bipartition. So we found a particular bipartition, and hence the graph G is bipartite. So let's look at the next part of the question. So the next part of the question is to prove that G does not contain a Hamiltonian circuit. So how do we tackle this? Well, remember, unlike Euler circuits, there's not an easy condition for Hamiltonian circuits. Okay, so one thing we can attempt is contradiction. So we can start by assuming, so suppose G has a Hamiltonian circuit H, okay? Has a particular Hamiltonian circuit H. Well, how do we find a contradiction here? Well, let's look at the facts we know about G. Well, one thing we know about G for certain is that it's bipartite. Okay, it's a bipartite graph. And if we look at our theorems of bipartite graphs, it says that a theorem is bipartite if and only if it only contains cycles of even length. If and only if it only contains cycles of even length. So notice that a Hamiltonian circuit should also be a cycle. Okay, so what that means is, what if we show that this Hamiltonian circuit has an odd length? If the Hamiltonian circuit had an odd length, then we would have found a cycle with even length. Sorry, with odd length, my bad, which would have contradicted the fact that a bipartite graph only has cycles of even length, okay? So what we're going to show is, what is the length? Well, the question we're asking is, what is the length of H? What's the length of H? Okay. Well, the length of H, let's think about it. Well, we have 9 vertices, okay? 9 vertices in the graph, okay? So the length needs to be 9, okay? The length needs to be 9 because why? We're connecting every vertex together using adjacent edges. The number of edges we're using has to be 9 with a Hamiltonian circuit. Now, if it's 9, so the length of the Hamiltonian circuit, so length of H equals 9. Well, that is a contradiction. There's a contradiction to the fact that if G is bipartite, it can only have cycles of even length. So this is a contradiction because if a Hamiltonian circuit did exist, then it would be a cycle of odd length. Okay, therefore we've proven that G cannot contain a Hamiltonian circuit. Okay, which this implies that G has no Hamiltonian circuit. Okay, now if the question was instead, if we had a different graph and the question was prove that there does exist a Hamiltonian circuit, well, the only way to prove that a Hamiltonian circuit exists is to actually give the Hamiltonian circuit. So if we found a particular Hamiltonian circuit, to prove that a Hamiltonian circuit exists, we could just provide that specific Hamiltonian circuit. Okay, so we're gonna move on. So we already looked at Euler circuits, Hamiltonian circuits, bipartiteness. Well, what about planarity? So planarity is another property of graphs, and says that a graph is planar if and only if you can draw it in 2D without crossing edges. One thing to note is that with planarity, you can always redraw it. Well, if a graph is planar, you can always redraw the graph so it looks planar. So, for example, this particular graph does not look planar. It doesn't look planar, right? Because there's intersection. Look. However, I could always redraw the graph so it looks like this. So I keep one of the diagonals, but instead of going inside, the next diagonal can go outside. Okay. So notice that this is exactly the same graph G, except I've drawn it in a planar representation. So planar, if a graph is planar, it might have a representation that doesn't look planar, but you can always redraw it so it does. And we have some more theorems for planar graphs. So some theorems we have is that if a graph is planar, then these inequalities need to be true. So these particular inequalities need to be true. So the first inequality is E less than or equal to 3v minus 6. And the second is E less than or equal to 2v minus 4 if G has no cycles of length 3. Okay, so these properties are most useful for proving a graph can't be planar. Because if these inequalities weren't followed, then the graph can't be planar. So another useful theorem for planar graphs is Euler's formula for planar graphs. And it says that V minus E plus R equals 2. So what is R? That is the number of regions in a planar representation of G. Now, if we look at a planar graph, what are regions? Well, regions are just areas separated by edges. So for example, we have a particular region here, okay, because it's separated by these 3 edges from this other region here. And that's a region, and that's a region. So in this case, we have 4 regions. Now, another interesting fact is that we can extend the handshaking lemma for regions, but instead of vertex degrees, we're looking at region degrees. So a region degree is simply how many edges are adjacent to a certain region. For example, if we put the region R1, notice that there are 3 edges adjacent to it. Okay, so we can say that degree of R1 equals 3. Okay, which means if we checked, or we could check that the handshaking limit makes sense. Okay, so if we added all those region degrees, then we get twice the number of edges. Okay. Now let's go into a question and see this in action. Okay, so this is a particular question here, and it's asking, given this certain simple graph, okay, show by redrawing that K is planar. Okay. Part B is calculate the number of regions in any planar representation of K. And part C is verify the handshaking lemma for regions using the graph K. So let's go ahead and look at part A. So we want to redraw the graph so it's planar. So what I'm going to do is first draw the original graph. Okay, I'm going to first draw the original graph. So it has these 3 vertices here, 2 up here, and 1 here. Okay, and if I fill in the edges, it looks something like this. So the first thing to do is look at where the problems are. Let me just label these vertices in quickly. That's A, B, C, D, E, F. Okay, so the main thing to look at is where are the problems arising? Okay, where are the problems arising? Well, that's where the intersection is, and the intersection is over in this particular area here. Okay, so all we want to do is redraw the graph so we don't have this intersecting problems, these intersecting problems here. So first thing I'm going to do is redraw the graph without the main intersecting problems, I guess, those 2 edges that are intersecting. So the particular edges I'm talking about are BC and AE. So I want to draw the graph without those edges first. So what I get is this. Okay. Now I need edges BC and AE. Okay, but how do I redraw them? Well, why don't I just draw BC in first? So obviously the problem here is that BC first, or it intersects with AD. Okay, but what I can do is draw it like this. Okay, so it clearly doesn't intersect with AD. Now the next edge I need to draw in is AE. Well, if I drew it inside, then there would clearly be some sort of intersection going on. So what I need to do is actually draw it outside of the graph. And that won't cause any problems because I can just go outside here, avoid B, and get to E like that. Okay, and this is the exact same graph K. Okay, yet it's drawn in a planar representation. So by drawing it in a planar representation, we've proven that K is a planar graph. Now let's look at part B. Part B is calculate the number of regions in any planar representation of K. Calculate the region. So what we can do to calculate number of regions is just use Euler's formula. Okay, we know that V minus E plus F equals 2. Hence, sorry, F, that should be R. Hence, R equals 2 plus E minus V. So all we need to do now is calculate or determine E and V. Well, we can just count from the graph. So the number of edges is So the number of vertices is 6. Now the number of edges is just going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 here plus 8 minus 6. So it's 10 minus 6 gives us 4. So there are 4 different regions. And we could have verified there are 4 regions by just finding the regions on the graph. So that's R1, R2, R3, and R4. Okay, so there are indeed 4 regions. Now, part C, verify the handshaking lemma for regions with K. Well, all you need to do is find the region degrees. So degree of R1 is the number of edges adjacent to it, and we can count those. Which is going to be 1, 2, 3, 4. Okay, so that's 4. Now degree of R2, what is that going to be? That's just going to be, again, 1, 2, 3, 4. Now degree of R3, let's go ahead and look at that again. That's going to be 1, 2, 3, 4. Okay, so that's 4. And now the degree of R4 is just going to be 1, 2, 3, 4. So counting all of those edges at the edge of the graph. So that's 4. So if we add them all together, we get 16, which is exactly 2 times 8, where 8 is the number of edges. Okay, hence the handshaking lemma holds. Now the next part to move on to is graph isomorphism. Graph isomorphism. Okay, so let's look at the definition of an isomorphism with graphs. So let G and G dash be graphs with vertices V and V dash, and edges with E and E dash. Then G is isomorphic to G dash if and only if there are 2 bijections, one from the vertex set to the other vertex set, and one from the edge set to the other edge set, such that E is incident with V and G if and only if G of E is incident with F of V in G dash. Okay, so what is that saying? Well, this means that this essentially means that 2 graphs are the same except for how the vertices are labeled. Okay, and drawn, I guess. So if we break down this definition, that's kind of saying that there's a function from the vertex set in G. So if I take some vertex in the vertex set of G, what I get is another vertex out, say V dash, okay? Now I can also do the same with every edge in the graph. So I could take a certain edge and I'll get an E dash out, okay? Now we can, these graphs are only isomorphic to one another if and only if every V dash is incident to E dash if and only if, I guess, V is incident to G. So it's kind of telling us that the relabeling of the graph is different, okay? And there's some sort of function from the vertex set and some sort of function from the edge set, which causes this relabeling, if that makes sense. So the easiest way to think about isomorphism is via the invariant properties of graphs, I guess. So if we take a certain graph G, okay, and we apply an isomorphism, okay, and get a new graph out, some properties remain the same under the isomorphism. So the number of these properties are called graph invariants. So invariant means they don't change under the transformation. Okay, so some particular examples of graph invariants are number of vertices, number of edges, okay, degree sequence or number of vertices of a particular degree, degrees of adjacent vertices, bipartiteness, connectedness, number of paths / cycles of a certain length, existence of Euler / Hamilton paths, and planarity. Okay, so all of these properties here are graph invariants, so under an isomorphism won't change. Okay, now graph invariants, if I prove that 2 graphs have the same graph invariants, it does not mean that they are isomorphic. Doesn't mean that they are isomorphisms of one another. Okay. However, if 2 graphs didn't have the same graph invariance, so for example, the number of edges was different, then they cannot be isomorphic. Okay? So I'll state that again. Basically, if we want to prove that two graphs or one graph is an isomorphism of one another, I can't just prove it by looking at all the graph invariants. I need to prove it by providing the specific bijection from the vertex set to the other vertex set, and the same with the edge set. Okay, so I need to provide, to prove that graphs prove isomorphism, I need to provide the specific transformation of function f, i.e. function. Okay. However, to prove two graphs are not isomorphic, I can just show that they have different graph invariants. Okay. Again, if I show that two graphs have the same graph invariants, they are not necessarily isomorphic. But if they had different graph invariants, they cannot be isomorphic. Okay. So one thing to look at before we move on to a question is, what is a homeomorphism? So a homeomorphism is given by this definition. So two graphs are homeomorphic if and only if they can both be obtained from a common graph by elementary subdivisions. Okay, so let's look at that. So if I have a particular common graph, so let's say I start with this graph here. Okay, fairly simple graph. Okay, what is a graph? What is an elementary subdivision? Well, an elementary subdivision is sort of taking one edge and adding a vertex in the middle. Okay, so what I could do is, say if this was A, B, C, D, what I could do is turn AB into two different edges with one vertex in the middle. Let's call it E. Okay, so this is an elementary subdivision. Okay, all right. But what I could have also done was, instead of dividing AB, I could have divided CD. Okay, so I might get this new graph as a result. Okay, so let's say E is here. Okay. Notice that they both are obtained from a common graph, so it would be homeomorphisms of one another. Something you can also notice is that these graphs are actually also isomorphic because they have the same, well, they're the same graph, just labeled differently. Okay. Now, the reason why we sort of introduced the notion of a homeomorphism is Kuratowski's theorem. So Kuratowski's theorem says that a graph is planar if and only if it does not contain a subgraph homeomorphic to K33 or K5. So K33 is the complete bipartite graph. With 3 and 3. So one set has 3 vertices, the other disjoint set has 3. Now K5 is a complete graph with 5 vertices. So that means that every vertex is connected to every other vertex in the graph, not including itself. Okay, so let's move on to a question and put this knowledge into action. So this is from 2021. The question is, show that G and H are isomorphic by finding an isomorphic vertex mapping between them. Okay, again, to prove that two graphs are isomorphic, we need to provide the specific isomorphic graph vertex mapping. Okay, so to do that, let's look at graph invariants to sort of help us out. Okay, so first of all, something we can look at is degrees. Okay, so B has degree 1 and C has degree 1. So these are both degree 1. Okay, now under the isomorphic graph vertex mapping, these degrees need to remain the same. Okay, these degrees need to remain the same. So let's look at which vertices have degree 1 in the graph H. And the answer is Y and W. Okay, so these have degree 1 as well. So something we know immediately is that B and C need to be mapped to Y and W, but we don't know which one specifically. Okay, now how do we determine that? Well, notice that C is adjacent to a vertex with degree 2. Okay, C is adjacent to a vertex with degree 2, whereas B is adjacent to a vertex with degree 3. Okay, so again, this is graph invariance. Under the transformation, okay, B needs to transform to a vertex that is adjacent to a vertex with degree 3. Okay, now let's look at the particular graph H. Well, we can see that V, degree of V, equals 2, and degree of X equals 3. Okay, what does that mean? Well, immediately we know that C needs to map to W. Okay, why? Because W is adjacent to a vertex with degree 2. Okay, whereas Y is adjacent to a vertex with degree 3. Okay, but that also means we know that B maps to X. Oh, sorry, not X, Y. Okay, because again, Y is adjacent to a vertex with degree 3. Now, in terms of those vertices, we know that clearly A needs to map to V. Okay, all right, because A is adjacent to C and V is adjacent to W. Okay, similarly, we know that D needs to map to X. Okay, for the same reasoning. So the only two vertices we have left are F and E and Z and W. So Z and U. Now, how do we figure this out? Well, F has a degree, so degree of F equals 2 versus degree of E equals 3. So degree of E equals 3. Now in this graph, degree of U equals 2 and degree of Z equals 3. Okay, hence we can conclude that F maps to U and E maps to Z. Okay, so we provided the specific isomorphic vertex mapping. So we can only prove that they're isomorphic by providing the specific mapping. Okay, so let's move on to 2013 question. So show that the above graph is not planar. So how do we prove a graph isn't planar? Well, the first thing we can check is the inequality. So we can check whether E less than or equal to 3V minus 6 holds. Let's check if this holds or not. Well, to do that, we need to count the number of edges. So the number of edges is going to be 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5, 6, 7, I think. Let me just make sure I didn't make a mistake. Wait, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oops, that was completely wrong. 12. Okay, and now the number of vertices is going to be 6. Okay, so we check in our calculator or just do it by hand. So 3v minus 6, okay, is going to be 3 times 6 minus 6, okay, which is going to be 18 minus 6, which is 12. So we can see that 12 is less than or equal to 12. So the inequality does actually hold. So holds. Which means it could be planar, okay, but we're trying to prove it's not planar. So that didn't help us, okay. If the inequality didn't hold, then we would be okay. We would have proved that it's not planar, but right now we haven't proven anything yet. So it could still be planar yet. So now we're going to have to move on to a more powerful method, and that's Kuratowski's theorem. So again, we can prove that a graph is planar if and only if it does not contain a subgraph homeomorphic to K33 or K5. So another way of thinking about that is if the graph did have a subgraph homeomorphic to K5, okay, so if G has subgraph homeomorphic to K5, then then it cannot be planar. Okay, so to look at this, what we need to do is first, well, compare the graph to K5. Let's look at the graph in K5 and let's see how we can compare them. Okay, so K5, well, obviously K5 has 5 vertices. Okay. Okay, and in terms of connectivity, they're all connected to one another. So Jordan. Okay, something like that. Now the graphs kind of look similar, but the main problem is that this graph has 6 vertices. Okay, 6 vertices. Well, what we want to do is sort of prove that a subgraph is homeomorphic to K5. So what we're going to do is do the opposite of showing, sort of do the opposite of this elementary graph subdivision. So we want to do the opposite of an elementary graph subdivision, and we kind of want to absorb a vertex into a current edge, if that sort of makes sense. I'll demonstrate what I mean. So, well, the main difference between these two graphs is this sort of area over here. Okay. What we need to do is remove the vertex C and remove the edge CF. Okay. So what we want to do is transform this graph via the opposite of an elementary subdivision into this. So we want to remove, so this is B, A, E, D, F. We want to remove C and we want to remove CF. So how can we do that? Well, we can introduce a new edge, BD, and absorb C into this new edge. So we've sort of absorbed it into this new edge. Now, what I can do is introduce all the other edges that were already there. Okay. Okay, and notice that what we have is something isomorphic to K5. These are the same graph, just they look different. Okay, so they're exactly the same graph, which means that what we've shown is that there is a subgraph homeomorphic to K5. And that means by Kuratowski's theorem that it is not planar. Okay? So again, what we did was the opposite of an elementary subdivision. So instead of adding new vertices, we remove vertices by absorbing them into edges. Okay, so that's the opposite of an elementary graph subdivision. So by Kuratowski's theorem, this cannot be planar. So let's move on now to the notion of an adjacency matrix. So an adjacency matrix, well, if a graph G is an ordered listing of vertices V1 up to Vn, then the adjacency matrix is an n by n matrix with each entry Aij being the number of edges connecting Vi and Vj. Okay, and now why is an adjacency matrix useful? Well, if we take the kth power of an adjacency matrix, the ith row and the ith column value, so i.e. Aij to the power k, is going to be the number of walks between Vi and Vj that is of length k. So for example, if I had A23, okay, squared, then that would be the number of walks between 2 and 3 of length 2. Okay, so it's really useful because it allows us to find the number of walks between two vertices with a certain length. So let's go ahead and look at a question now. So this question from 2021, a graph G on the vertices A, B, C, D in that order. So an important thing to notice is that adjacency matrix, we need to have order. Now the part A is, does the graph have any loops? And if so, which vertices have loops incident on them? Well, loops are sort of edges connecting a vertex with itself. So if I have a particular vertex like this, we can see that this needs to be true. Why? Because if we look at the 1, 1 entry, okay, this is the number of edges connecting the vertex A with itself. Vertex, number of edges connecting A and itself. And we can see that we have a non-zero value, which means there has to be one edge connecting A and itself, i.e. it needs to have one loop. Now, in general, the main diagonal sort of tells us the number of edges connecting a vertex with itself, and you can see that we all have non-zero entries along the main diagonal. Okay, all are non-zero entries. All non-zero on main diagonal. Okay, so what that means is that there are loops, and specifically every single vertex, sorry, A, B, C, and D have a loop on them. Why? Because if we look closely at the matrix, clearly A has a loop, B has a loop, C has a loop, and D has a loop because they're all non-zero. Now let's go ahead and look at part D. So find the number of walks of length 3 from the vertex D to the vertex D. So to find number of walks between vertex D and itself, what we do is simply take the matrix to the power 3. Now this is a not so simple calculation because it takes a bit of work, right? But if we, for example, found this matrix using Maple or something, we can see that we would get this. So m cubed is equal to this. So this is m cubed, sorry. Okay, and now the number of walks from D to D is going to be the entry in the fourth row and the fourth column. Okay, why? Because that entry there tells us the number of walks from D to D of length 3. Hence, there are 46 walks of length 3 from D to D. So let's move on to another question now. So given M is the adjacency matrix of this above graph, where the vertices are labeled in numerical order. Now, it is given that the 1, 1 entry of the m to the power 14 matrix is 429. What does this tell you about the graph? So the entry of the m to the 14th matrix, the 1, 1 entry is 429. What does that tell us? Well, it tells us that if we look at walks of length 14, there need to be 429 walks of length 14, that go from 1 to 1. Okay, that's by a definition of the powers of the matrix. So clearly there are just 429 parts of length 14 from the vertex 1 to the vertex 1. Now part B, prove that if n is a positive even number, then the 1, 1 entry of m to the power n is non-zero. So to do this, we're going to have to look at the graph in more detail. So first of all, if we take m to the power n, where n is an even number, that is the number of lengths, number of walks of length n from 1 to 1. So to look at this in more detail, well, we can say that n equals 2k, where k is a positive integer. Okay. Now, why do we? Well, the question is, asking us to show that the 1, 1 entry is non-zero. So that's equivalent to showing, or equivalent to explaining why there is at least one walk of this length from 1 to 1. How do we know that's the case? Well, if we look at 1, right? To get to 1, well, we can go to 2, and from 2, what we can do is go from 2 to 1 again. Similarly, we could go from 1 to 2, and 2 to 3, and then 3 to 2, and then 2 to 1. Now, let's look at the lengths of these parts. Well, they're always going to be even. Why? Because there's 1, 2, 3, 4. And more generally, if I go from 1 to, let's say, k, where k is a positive number, so I reach k, the number of steps in the first one, okay, sorry, let's say we'll go to k minus 1, my bad. So the number of steps, k plus 1, k plus 1, the number of steps is going to be k, okay, because 1, 2, 3, 4, up to k, okay? Now, clearly, to get back to 1, what I need to do is go in the opposite direction, okay? To go to the opposite direction. Now, that's going to introduce another k. Okay, so in total, I've gotten k plus k equals 2k, which equals n. So that's the length of the path. And you can see that we can always do this, okay? And now if k is larger than the length of the graph, what I can just do is add repeats. So I could just add a repeat from from 3 to 4, and then 4 to 3, and then I could go again from 3 to 4, and then 4 to 3. And I can keep doing this until I'm okay to go back to 1. Okay, and you can see that these will always be even length parts. Okay, hence there is always a non-zero entry in the 1, 1 column, 1, 1 entry, of the matrix m to the power n. Okay, now part C, find the smallest odd n for which the 1, 1 entry of the matrix n to the power n is non-zero, and give reasons for your answer. So let's look at the graph. I'm just going to draw it out again on this page. So the graph is going to look like something like this. So this is 1, 2, 3, and a dot, 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 all the way up to 1079, 1079, 180, 1081. Okay, and you can see that 1081 has a loop that connects back to itself. So anything, let's just think about how we can construct a path of odd length. So the question is essentially asking us to find the smallest length of a odd path. So construct an odd path with the shortest length possible. Because that would tell us the smallest positive odd n for which the 1, 1 entry is non-zero. So how do we do that? Well, notice that all of the paths that we constructed earlier, okay, to something less than 1081 were always even length. Okay, they always had to be even length. Well, how do I construct odd length? Well, I'm going to need to use the loop here. I'm going to need to use this loop here. Okay, why? Because that loop allows us to enter or add a +1 to our path, which will give us an odd. So everything previous will give us an even number, and then we +1 here will give us an odd length in total. Okay, so what's the smallest? What is this the smallest path with odd length? Smallest walk, sorry. Well, it's going to be from 1 to 2, 2 to 3, all the way up to 1079 to 1080, 1080 to 1081. Now the length of that path is going to be 1080. Okay, now we +1 because we go from 1081 to itself, and then we go back, it's going to be another path of length 1080. Okay, so what I get is 2161. Okay, 2161 is the length of the shortest odd path. Hence, if we take m to the power 2161, we will have a non-zero entry for 1, 1. So now that we're done with this question, let's move on to the last part of graph theory, which is weighted trees. So a tree is a simple connected graph with no cycles. Something to notice is that a tree with n vertices has n minus 1 edges. Okay, and also if we have two or more vertices, we need to have two pendant vertices, so vertices with degree 1. Now a spanning tree is a subtree that contains every vertex of the graph. And a weighted tree is a tree whose edges have been given numbers called weights, and then the weight of an edge E is denoted W of E. And now the weight of a graph G is the sum of all the weights. So looking at a spanning tree, I'll just give you a quick example of a spanning tree. If I have a particular graph that looks like this, for example, okay, a spanning tree is going to be a tree that contains every vertex of the graph. So a tree needs to look something like this. So this would be a tree, okay? Because I have 1, 2, 3, 4, 5 vertices and I have 4 edges. So that's a particular tree and it connects every single vertex of the graph. So that's the spanning tree. Now, Kruskal's algorithm is used to find the minimal spanning tree. So that's a spanning tree with the lowest sum of weights. Okay, and now there's a nice stepped process to finding the minimal spanning tree. And that is to start with T, which is the empty tree. Now part 2 is to sort the edges in increasing weight. Now going down the list, add an edge to T if and only if it does not form a circuit with the existing edges, and continue until T has n-1 edges, because this will give us a tree. So let's look at this algorithm and process. So in process, we can always do this efficiently using a table. So I'll show you what I mean. But given this particular tree here, okay, use Kruskal's algorithm to construct the minimal spanning tree for the above weighted graph. Okay, so what we want to do is first start with the empty tree. Okay, so I'm just going to label all these vertices in. That's B, that's A, that's C, that's D, that's F, and that's E. Okay, the empty tree. Now, what I want to do is then assort the weights in ascending order. So in increasing weight. So I'm gonna start by like writing out all of these edges and writing in brackets, their weight. And if I did that, what I would get is what I should do is construct this table with edges in increasing weight. So this is kind of a bit of a long process, but it's necessary. So we need to sort them in increasing weight. So look at the graph. I'll see DE has a weight of 4, BE has a weight of 4. Put them in my table, they have weights of 4. Okay, and I will do the same for every edge in the graph. Now, to actually apply Kruskal's algorithm, I first look at the first edge that I've put in the graph. Okay, and to figure out whether I add it or not, the question is, does it form a circuit with the existing the existing edges? So there's no edges, hence it won't form a circuit, so I can add it. So what I'm going to do is add BE. Okay, and that has a weight of 4. Now let's look at DE. If I add DE, does that add a circuit? The answer is no, because clearly there's no circuit there, so I can add it. Now AF has a length of 5. Now the question is, can we add it? So if we drew it in, does it form a circuit? No, it doesn't. So there are no problems there. Now let's look at EF with a weight of 5. So EF looks like this. The question is, does it add a circuit? The answer is no, because still we can construct no circuits within this graph or this tree. So that's all good. Now EF has a weight of 5. The question is, can we add it? Let's look at, oh sorry, not EF, we already did add it. We're looking at AE now. AE has a weight of 6, can we add it? Well, the question is, well, the answer is no. Why? Because clearly we could construct this following circuit. Okay, so we can't add it, so we're going to exclude it from the tree. So we're going to exclude AE. Now BC has a weight of 6. Can we add it or not? BC, the answer is yes, because it has a weight of 6 and it does not add a circuit. Now we are done. Why? Because we've got 1, 2, 3, 4, 5. We've got 6 minus 1, n minus 1 edges, and we've also got a minimal spanning tree because it connects every single vertex in the graph. Hence, we're done, and we don't have to worry about any of these other ones. So this is our minimal spanning tree. So in terms of exams, I've looked at the question bank, and most types of these sort of weighted tree questions or involving Kruskal's algorithm are, well, obviously we can't draw the graph on Mobius exams, but they do ask, I saw a question where it asked you to select the edges that would be included in the graph, so that would be sort of reminiscent of this table. Also, I saw a question which was, given this graph, what is the lowest sum of weights? Sum of weights for a spanning tree, or equivalent, what is the weight of a minimal spanning tree? So you have to use Kruskal's algorithm and then simply add all these weights in the minimal spanning tree together. So those were the types of questions I've seen in the Mobius exams. So now let's move on to the last part of the seminar, and that is Dijkstra's algorithm, which is used to find the minimal spanning tree with respect to a particular vertex. So that's sort of answering the question, if I start with a vertex, what is the tree that minimizes all the distances to other vertexes, if we think about weight as representing distance? So in terms of Dijkstra's algorithm, the steps are, start with the subgraph T containing only the given vertex A. Now consider all edges incident to A. So these are what are called candidate edges. So all the edges that are incident to A. So all edges that we could possibly add to the graph. Now of these edges, choose the edge with the lowest weight and note down the vertex B which it leads to. Okay, now we connect B and A together, okay, via an edge. So connect. Okay, now we have more candidate edges because now we are at B. There are more possible edges we could add to the graph. So we have more candidate edges. Again, out of all those candidate edges, we'd pick the one with the lowest weight. Okay, and we keep doing the same until we've connected all the vertices of G. And then we've got a spanning tree. So let's apply Dijkstra's algorithm. So again, similar to the Kruskal stuff, questions involving Dijkstra's algorithm would be, select the edges that would be used in a minimal spanning tree with respect to a certain vertex, and also, what is the lowest distance between A and a certain other vertex. So we could use the minimal spanning tree with respect to A to help us out there. So let's apply Dijkstra's algorithm. So what we want to do is first start with A. So we first start with A. Now to continue, what we need to look at are the possible candidate edges. So the candidate edges are AB, AE, and AD. So what we want to do is construct a table and write them out in the table, including their weight. So we write them out, including their weight. Now, out of all of these edges, the one with the lowest weight is going to be AE. Okay, AE, because it has a weight of 1, which means the next vertex we connect to is E. So we have E here, and we've connected to E. And what we're going to do is label that weight is 1. Now to continue, what we want to do is look at the new candidate edges. So once we're at E, we introduce new candidate edges, namely these 3 edges. So now the total number of edges we have in our candidature are AB, AD, BE, DE, and EC. So I've written them out here. So we add all these new candidate edges. So everything in this row here. So that means that we're going to look at the one with the lowest weight, that is AD, which means the vertex we connect to is D. Okay, so we've connected to D, okay, and that has a weight of 2. So once we've connected to D, let's look at the new candidate edges we add. The only new candidate edge we add is DC. Okay, so we can add that into our list. Now clearly the lowest length we have is going to be ED or EC. So ED or EC. Now we have to pick the one that doesn't give us a circuit because we're looking for a minimal spanning tree. So clearly ED gives us a circuit. So what we need to pick is EC. Okay, so that has a length of 3. So we're going to pick EC. So that connects us to C. And now in terms of new candidate edges, we have one more candidate edge, and that will be this edge here. Okay, which means that if we look at our new candidate edges, the one with the lowest length or the lowest weight is going to be let's see, so EC or CB. Oh, sorry, with respect to A, we want to find this one. It's going to be EB. Whoops, sorry, out of all this list we have EB. Okay, which means we're going to connect like this. So everything's with respect to A. Okay, and that has a length of 3, which means that we are now done because we've constructed the minimal spanning tree. Okay, that is the end of the seminar. So thank you everyone for coming, and thanks for Mary and Michael for presenting the previous parts. If you have any questions about this seminar, feel free to put it in the chat or use the Discord server. And in general, good luck for the exam, and study hard. Thanks a lot for coming.